Hello students, welcome back. In this lecture we're going to talk about derivatives of our monosaccharides. And our first derivative is going to be a sugar alcohol. It's going to be a sugar alcohol. It's going to be our first derivative. Okay, and I'm going to start with an aldose. A hexose, 3, 4, 5, and 6 CH2OH. And this is going to be our aldose. Now, what we're going to do to this aldose, well, let's just go ahead and use glucose here. So, right, left, right, right, Fisher projection for glucose. And what we're going to do, we're going to actually reduce the aldehyde functional group. When we talked about the acids as before, when we talked about glucuronic acid, glucaric acid, those were oxidations. Here we're going to perform a reduction. So we're going to have a reduction here. We're going to reduce this aldehyde functional group. And when you reduce an aldehyde functional group once, you get an alcohol. So it's going to be, I'm going to save that one. 2, 3, 4, 5, and 6 CH2OH. Right, left, right, right. And so we're going to actually reduce this aldehyde functional group. And again, when you reduce the aldehyde functional group, you create an alcohol. And I'll just put the OH group up here just to show that it doesn't matter. It's achiral. It doesn't matter which side it's on. And so when we do this, we convert the aldose to an alditol. An alditol. And so since this is D-glucose, we create glucitol. And glucitol is a sugar alcohol. Now, glucitol is known by a more common name, and that is sorbitol. Sorbitol is an artificial sweetener, and it's used in a lot of sugar. It's used just as a substitute for a lot of sweet products. So it's an artificial sweetener. Artificial sweetener is sorbitol. Now, sorbitol is great, but there is one reservation for using sorbitol, and I'm going to explain that now. In your eyes, I'm going to just draw an eye here, cross section of an eye. Okay, that's going to be our cornea here, and let's make our pupil. That's the hole in the eye. Retina back there. Okay, this hole here, this is the pupil. That doesn't really matter. But in front of the pupil, this is what we want to see. In front of this pupil here, this is the lens. And the lens is supposed to be very soft, pliable, and clear. Completely transparent. However, when you consume a lot of sorbitol, the sorbitol actually builds up. It builds up within the pupil. And when it does, when that sorbitol builds up in the pupil, in the lens, it builds up in the lens. And it causes the lens to become cloudy and hardened. And that condition is known as cataract. And this happens a lot in diabetic patients. So it's called diabetic diabetic cataract. Okay, so that's a condition you have to look for. If you're going to go into the medical field, you're going to encourage your patients to not consume so much sugar. If they intake a lot of sorbitol, that can still cause them a problem. So here is our first sugar alcohol, sorbitol or glucitol, and alditol, a sugar alcohol. On the next clip, we'll explore, I think we'll explore 2 more sugar alcohols, but now that you know what they are, we'll just be able to show you those structures.
Okay, on this clip, I'm going to show you 2 more sugar alcohols. Let's see, the first one is going to be based on the 2-epimer of glucose. So let's look at another sugar alcohol here. Move some things. Okay, here we go. Our aldehyde group. That's 1, 2, 3, 4, 5, and 6 CH2OH. Now, I'm going to draw glucose first, but I'm going to erase something. So if you're writing with a pen, you may want to wait. So right, left, right, right. That's glucose. But I'm going to draw the 2-epimer of glucose. So what I'm going to do, I'm going to get rid of the OH on this side. I'm going to put the OH over here. So the 2-epimer of glucose is called mannose. So this sugar is mannose, and mannose is, of course, it's an aldose. And all we're going to do, again, is reduce. I'm going to have a reduction here. And when we reduce this, that's 1, 2, 3, 4, 5, 6. Okay. And again, it doesn't matter. Well, I'm going to save that one. I like to save that one. I don't know. It doesn't really matter. So we have left, left, right, right. I'm going to do these first. And this one is over here. Now, OH. Now, this sugar alcohol derivative of mannose is called mannitol. And again, another sugar alcohol. Not a lot to say about mannitol, but it is a sugar alcohol. Okay, let's do one more. We'll look at these later. We'll see it later on, but for now, nothing significant about mannitol. Let's do one more sugar alcohol. This is a pretty famous one that we're going to draw. It's a triose. And so it's going to start out. The aldose is a triose. And so there's our aldehyde. Okay. And then this is D-glyceraldehyde. Now, glyceraldehyde is different from all the other aldoses because glyceraldehyde, I misspelled that. Glyceraldehyde doesn't end with the suffix -ose. It should be called D-glycerose, but it's called D-glyceraldehyde. And so, for this one here, we just think about aldehyde. We treat the word aldehyde or the suffix aldehyde just like ose. Okay, and now let's reduce our aldehyde group, and then we're going to get, wow, that's awful. That's 1, 2, 3, and this derivative is just has, oh, I don't need that. This derivative has 3 OHs, and so we call this glycerol. And glycerol is found in lipids. It's really prominent in lipids. And glycerol is a sugar alcohol. It's a sugar alcohol. Okay. And again, there's a reduction here. And that's all that we have to say about our sugar alcohols. Just remember, for your sugar alcohols, you reduce the aldehyde group to an alcohol. Our next sugar derivative is going to be a deoxy sugar. A deoxy sugar. And I'm only going to show you one of these, so this won't take very long. Let us start with our parent sugar. We're going to draw ribose in the furanose form. So here we have, that's carbon 1, 2, 3, 4. That's carbon 4 there. And I'm going to close the ring. And this will be carbon 5, CH2OH. And then this goes down, down. And let's draw beta. And so this is OH. And we will show our hydrogens here. And so this compound is, we could just say this is beta D ribose. But if we wanted to be sticklers about this, we would call this beta D ribofuranose. We could call it that, but for now, let's just call it beta D ribose. And I don't really even care if it's beta or alpha now. The point that I need you to get, okay, let's see here. Let's number these carbons. That's 1, carbon 2, 3, 4, carbon 5. Okay, the point here is you're going to lose the hydroxyls on one of these carbons, and it's going to be carbon number 2. So now I'm going to redraw this here as our oxygen. That's carbon 1, 2, 3, 4, and close the ring. CH2OH. OH. And now here we're going to have just an H. And we'll leave it beta here. Don't really care if it's beta or alpha now. Okay. And let's put our H's. So this is 2-deoxy. 2-deoxy. Because there's no oxygen here. 2-deoxy beta D ribofuranose is what it would be, but we're just going to put ribose. 2-deoxy beta D ribose, or just 2-deoxy D ribose. I don't really care if it's beta or alpha, but the important point is, this is what's important. This is what you need to know in your heart of hearts. Ribose is found in RNA, and deoxyribose, this is the sugar that's found in DNA. You have to know that. That's something you have to know, because when we get to our nucleic acids, we're going to really talk about these sugars and how they're numbered and how they're bonded. And so you really need to know the numbering. So this is always 1, 2, 3, 4, 5. And again, it's best to always draw your ring carbohydrates with that anomeric carbon on the right side if you can, because more people will more often recognize it in that form, putting that anomeric carbon over here. But for some, when you're making certain disaccharides, you have to flip it over. Like for things like sucrose, you have to flip that fructose over. But for here we have 2-deoxy beta D ribose, the sugar found in DNA, the molecule of life. Well, can't really say that. Some people say water is a molecule of life. So for me to say DNA is a molecule of life is like taking away from water, stealing from water. That concludes this clip. Before we discuss more carbohydrate derivatives, I need to go over functional groups with you. And we'll do this several times. We'll go over functional groups several times throughout a course like this. Like, for example, I don't know what course this is, but if this is biochemistry, of course we'll talk about functional groups several times because they always come up. And so let's talk about the various functional groups that we may find. Okay, here we are, functional groups. Okay, now I'm going to identify 3, 4, 5, 6, 7, 8, 9, 11, about 11 functional groups. And they're really shouldn't be too difficult. So if you have this functional group here, CH3 attached to something, we call this the methyl. We call this functional group the methyl group. And that makes sense. And we've seen this one already. Most of these we've seen. If we have OH attached to something, we call that OH, the hydroxyl group. And we've seen it makes alcohols. If we have a carbonyl carbon attached to a hydrogen here, we call this entire functional group, we call all of this an aldehyde. And we've seen this one already. Again, we've seen nearly all of these. If we have an R group here, well, let's do this. Yes, if we have an R, C, double bond O, and another R, we call this functional group a ketone. Okay, and again, all of these we've seen. I'm going to put this next one. We haven't seen it yet. I'm going to go ahead and put it. If we have R, O, R, this is an ether. And that may come up later. That functional group is an ether. And so those are the, oh, and one more that we've seen. I'm going to put a line here. Okay. And if we have NH2, we've seen this one already. This is an amino group. This is an amino group. Okay. And those are some of the common functional groups that we've seen. Well, let's do, I need the others to be, well, let's go ahead and finish the common ones. And if we have C double bond O, OH, we call this a carboxylic acid. This is a carboxylic acid. And if we have C double bond O, O minus, and if we lose the acid, we get the conjugate base of the carboxylic acid. And so this is a carboxylate. This is a carboxylate. What else is there? What else have we already seen? We've already seen this functional group. if you have a carbonyl carbon and it loses the carboxylic acid, we lose the H here and the H on the amino group. We form this, and this functional group is called an amide. This is called an amide. We can go and put an H here. And this is found in peptide bonds. This is a peptide bond. Okay, those are all of the common ones. Those are the ones we've seen before. Now let's go to something new. A new functional group. Now we've talked about phosphorylations of proteins. So if we have something like this, O, P, O, OH, OH. This is going to be, this functional group, of course, is a phosphoric acid. So a phosphoric acid can be attached to something here. And if we lose the proton, let's say we lose one of those protons, then this becomes a conjugate base. This becomes now a phosphate. Okay. And this would be a phosphorylation. When you put a phosphate on something, that's called a phosphorylation. Now, there are only two other functional groups left, and these are the important ones. These are the ones that are really prevalent, and you really need to know these. And so I'm going to start with our carboxylic acid again. So what's going to happen? The carboxylic acid, so really our carboxylate, there's our carboxylate. And so instead of putting a minus there, we're going to have a bond here. We're going to put an R here. And so this functional group is called an ester. And esters are found in, are very prevalent in biochemicals, especially in lipids. And so we'll have esters there. And if you start out with the phosphate, okay, here we have the phosphate, and what we're going to do here, we're going to add an R, and so this is a phosphoester. That is a phosphoester. And if we put an R on the other side, we'd get a phosphodiester, and that's found in nucleic acids. If we put another R group over here, and I'm not going to do that here, but if you put an R group right there, I'm going to erase it. That would be the red R. That would be a phosphodiester. Okay, and so I don't want to take a lot of time on this. I just want to introduce you to the various functional groups. So let's just go over them quickly. Functional group CH3 is a methyl group. OH, hydroxyl. C double bond OH, aldehyde. R, C double bond OR is a ketone. ROR is an ether. NH2 is an amino group. C double bond OH is a carboxylic acid. C double bond O without the proton is a carboxylate. C double bond O NH2, that's going to be an amide found in peptide bonds. If you add a phosphate here, that's going to be a phosphoric acid. We see these in phosphorylations, and if you remove the proton, you get a phosphate. And for your carboxylic acid, if you replace the H with an R, you get an ester. And for the phosphoric acid, if you replace the H with an R, you get a phosphoester, sometimes called a phosphate ester. And those are our functional groups, and we'll need to know those throughout. The last sugar derivative that we will explore in this lecture will be our sugar phosphoesters. And we're just going to look at 3 examples. 3 common examples of our sugar phosphoesters. Okay, so these are going to be our sugar phosphoesters. Since nearly all of the esters and sugars are phosphoesters, this is analogous to saying, or this is equivalent to saying the sugar esters. We'll be looking at sugar esters. And so if I ask you to draw a sugar ester, I'm talking about a sugar phosphoester. Or if you're reading in a paper or in your textbook and they're talking about sugar esters, more often than not they're referring to the sugar phosphoesters. We'll look at 3 very common examples of these sugar phosphoesters, or these sugar esters. Let's start with glucose in the ring form. So I'm going to draw glucose for you. CH2OH. Up, down, up, down. Okay, and let's put glucose in the alpha form. It doesn't matter here. We'll just put it in the alpha form. And everywhere else, I'm going to put the H's everywhere. Now, we all know that this is alpha-D-glucopyranose. But a lot of times when you're reading textbooks and you're reading papers, the author will not use the complete name of the compound of this. He or she will just call this alpha-D-glucose. And it'll be understood that it's in the pyranose form. So if I ask you on a test to draw glucose in the ring form, you would do it as the pyranose. Although you can draw it as the furanose if the hydroxyl on the 4-carbon is the one that attacks the carbonyl. And so this is alpha-D-glucose. And so what we're going to do now is add our phosphate to carbon 1. We're going to replace COH and put our phosphate. So let's draw this here. I'm going to move that over just to make sure I have enough space. CH2OH. Up, down, up, down. Okay, we're going to put our phosphate, put our H up here. Now the phosphate is going to go down. It's going to be O, P, O, O minus, O minus. Now, if we numbered our carbons, this would be carbon 1, 2, 3, 4, 5, 6. And the same would apply here. 1, 2, 3, 4, 5, 6. And so this new compound that we've drawn is a sugar phosphoester. I'm going to highlight the ester linkage here, and this is what makes it the phosphoester linkage. That's a phosphoester linkage. Now, if we name this, this would be called alpha D glucose 1-phosphate. And you'll see a lot of these phosphorylated sugars in metabolism, like in glycolysis. And I'm going to give you a whyness, or teleologically, why do you need to phosphorylate glucose or sugars? Okay, I'm going to go to another slide here, and I'm going to explain this very quickly. Let's say here we have a cell, and outside the cell you're gonna have sugars. Let's put here just a G for glucose. You're gonna have lots of glucose is outside of this cell, and what this cell is going to do, it's going to take the sugar inside of itself, and so now you're going to have a lot of and you're going to get to the point where you're going to have more sugar inside than is found outside. And so now it's going to be very easily for this sugar to diffuse back to the outside. And so one of the things that the body does, that metabolism does, is that it phosphorylates these sugars. And that phosphorylation gives them that big negative charge. It gives them a very big negative charge. And so now these sugars can't diffuse back out of the cell. That's why you see in metabolism, especially when we go with something like glycolysis, you'll probably do that in biochemistry too, these sugars can now not leave the cell. It traps them inside of the cell. And that's why you have these phosphoesters. Okay? And so this is our first phosphoester, alpha D glucose 1-phosphate. I'm just going to stop here for this one, and we'll come back on the next slide. On the next clip, we'll look at two more very famous sugar phosphoesters. We're going to conclude this lecture by looking at two more sugar phosphoesters. The parent sugar for this one is going to be fructose. So we're going to draw fructose here. That's 2, 3, 4, 5. Okay, and CH2OH, and we're just going to let's make it alpha CH2OH. Let's put now our hydroxyls OH, and we'll put this one down, and we'll have, that should be it, alpha D fructofuranose. That's the name of it, but for now we're just going to call it alpha D fructose. If we number these carbons, 1, 2, 3, 4, 5, 6. And remember, for fructose, the 2 carbon is the anomeric carbon, not the 1 carbon, because it is a ketose. Okay, now let's add let's make a phosphate ester using carbon 2. So we're going to use this OH to make our phosphate ester. No, let's not use that one. Let's use the 1. So I'm going to undo that. So we're going to put the phosphate. We're going to put our phosphate here. So let us draw fructose again. Okay, this is our furanose ring, CH2O and PO minus. So we're going to put a phosphate there. We're going to do something different here for fructose. So CH2O. We're going to put another phosphate over here. O. And we can complete our. So this is down. This is up. And we'll put our hydrogens. Well, we need to put this OH to make it alpha, and finish off with our hydrogens, H. And so we've doubly phosphorylated fructose here, and so this fructose has 2 phosphates on it. Now we could call this, so the name of this should be alpha D fructose. This 1,6. We could, since it's two of them, we could say diphosphate or biphosphate, either one. So let's just put biphosphate. Alpha D fructose 1,6 biphosphate. And if we number these carbons, we'll use green. 1, 2, 3, 4, 5, and 6. That seems to be a very reasonable name. Alpha D fructose 1,6 biphosphate. However, that's not the correct name. They don't use bi because these two phosphates aren't together. They're separated from one another. And so instead of calling it biphosphate, this compound is called bisphosphate. And so it's alpha D fructose 1,6 bisphosphate. And this compound is very important in metabolism again, especially in glycolysis. This is a metabolite found in glycolysis. Alpha D fructose 1,6 bisphosphate, and it is a phosphoester. A phosphoester. Okay. Now for our last, I'm going to go ahead and do the last one here. Our parent compound is going to be ribose. And so ribose, again, it is a furanose, just like the fructose we just drew. Okay, I'm going to draw ribose first. Remember, these both go down, OH, OH, and this goes up, CH2OH. And let's do alpha again, just to make our lives simple. And we'll put our H up here, H here, H here. And so this is alpha D. Now we know it's alpha D ribofuranose, but we're just going to put alpha D ribose. Okay, so that's alpha D ribose. Okay, and what we're going to do here, we're going to actually phosphorylate. Let's number our carbons. 1, 2, 3, 4, and 5. Here we're going to phosphorylate, or this is our anomeric carbon, but we're going to phosphorylate carbon 5. So let us draw the phosphorylated form of ribose. So we're going to have, so really when it's alpha, everything is down. So CH2, I'm just going to make all atoms of my phosphate red here. And that's it. Finish off with my hydrogens. Finishing off with my hydrogens because when you look at your notes, I want you to see the correct compound here. And so this is going to be, oh, I'm going to give you a chance. Can you name this? What's the name of this compound? Correct. I hope you're correct because I can't see you. Alpha D ribose 5-phosphate. And this compound is found in RNA. It's found in RNA and in nucleotides. It's found in RNA. Alpha D ribose 5-phosphate. And that concludes our sugar esters, or our sugar phosphoesters.